Welcome to the Todd and Noah Show, taking the mystery out of electric motors.
The mystery.
Mystery. Ooh, it sounds scary.
It does sound scary.
But little by little, we're going behind the dark closet, we're pulling back the curtain, and we're actually showing you that there's no boogeyman back there. It's actual just logic and common sense and components, and if you look at it correctly, you can take that mystery out of it.
And shall we say hello from sunny Tampa, Florida?
As always, we say hello from sunny Tampa, Florida, because we're in the warmth.
It's actually sunny today.
We wish you were here. It was really nice. It's actually nice. Very nice right now. We're having some beautiful weather. Once again, this is Noah Bethel, the Vice President of Product Development. I've been with the company for about 30 plus years now.
Ooh, going on 30.
Todd Gunderson, the Vice President of Sales and Marketing. I've been with PDMA Corporations for about 25 years. And this is our next, we left you last time with the cliffhanger about the Charlie Brown fault zone, which is insulation.
Yes. Why is everybody always picking on me?
Exactly. It's the one that everybody goes to.
The phrase is, the motor's grounded.
Everybody knows that insulation's bad.
Yeah. Yeah, but it's often...
Well, it's like you said, you were charged with going out to the fleet with a multimeter and a megometer.
Yes. And we would
save the world.
We would perform a megger on the motor, and at the end we would make decisions on that.
Yeah.
One reading we'd say, hey, it passed the megom test, and therefore it must be the pump.
Yeah. You know how many case studies we have where they've gone out and said, IEEE 43 says this motor's in good condition because of the resistance to ground, only to find out inductance is screwed up or
exactly. You
or
know,
resistance.
One really good credibility tool when it comes to insulation?
What's that?
The nose.
Ah.
And you've got an impressive one.
Are you calling me? I have a big nose.
I said impressive.
Hey, what's this?
If you can smell, if you've never smelled burning insulation, it's something.
Oh yeah, it's an acrid smell.
Just don't smell too much of it. It is dangerous.
Let me go in the corner and lick my wounds now. Moving right along, we'll get into the Charlie Brown. So can you give us a little history of insulation types and how they've changed throughout the years, Noah?
It's interesting.
On insulation
you go on
types?
and do a little research. It has come a long way. And everybody knows, like, when it comes to, like, electrical battles, you hear the battle between, like Tesla and that group, and that was a big deal, right? But insulation goes way back. And in fact, if I take it to the 1840s, one of the first forms of insulation to try to prevent, electricity from getting to a person or getting to ground was glass, right?
Really?
Yeah, just glass. And they were also using stuff like wood and silk materials, paper materials. Eventually,
just molding it around the wires.
Exactly, like just to do anything they could do to that, create some kind of insulating barrier. Eventually, it went to in the late 1800s into the 1900s into porcelain, and PVC and rubber became a normal insulating material. You've seen, some of the old stuff where they had the rubberized insulation going over the overhead because they didn't have hidden cables. They were actually just hanging them from the ceiling and stuff.
Yeah.
Today they're using stuff like epoxy resins and synthetic polymers and really state-of-the-art technology that gets in, firmly holds the windings, insulates everything as it should be, and you'll even get a test sample. You send a medium voltage motor into the shop and ask for a test sample. They're going to send you a cutaway of an additional set of windings that were placed in the VPI tank, send it to you for inspection. That's how critical it gets, because every turn needs to be completely insulated.
What about equipment changes like variable frequency drives? How has that affected insulation?
If you were to set in the PDMA technical support department for a day, and you did this, many years ago, the conversation was always, is it the pump or is it the motor? Electrical versus mechanical world. But I can tell you today, that has changed a lot, right? Today you sit in there and many of the conversations, if not in certain days, the majority of them are, well, let's look into see if this is the motor or the drive, right? That becomes a common question. And sitting through those conversations and hearing the troubleshooting, it really helps you to understand the interconnectivity of, can a drive affect the insulation? Can the insulation affect the drive? The answer being, of course, yes.
Okay, and then I've noticed differences with the polarization index curves with the way if it's an inverter duty drive rated winding versus, why is that?
Well, and a lot of it may not be just specifically inverter
Okay.
duty, but even the VPI process versus, like, say, the varnish process, right? A varnish, a dip and a bake, right? You're going to be a standard, a little bit different material than what they put into a VPI tank. And so it's not unusual for like a classic, let's say, varnish, dip and bake type process to result in a very gradual polarization index test with values, very commonly between 2 and 4 and passing the test, right?
Right.
And we'll get into some detail about that. But, we can talk a little bit about it. From a PI perspective, the 10-minute resistance to ground versus the 1 minute, we expect that, 10 divided by 1 minute reading to be around 2 to 5. And for your normal, dip and a bake type, process, that's not unusual to see.
Yeah.
But you get into these VPI, synthetic polymers and stuff like that, they will rapidly shoot up to hundreds of megs, hundreds of gigs even, into sometimes a tera-ohm range of resistance.
Does that have to do with the microsecond firing time on drives, that it has to be polarized that fast, or?
Not so much that. I don't
Okay.
think that the drive specifically, causes
So the
that.
firing sequence doesn't, the quick firing sequence doesn't
Well, I can tell
affect
you
it?
one thing for sure is that the rapid firing frequency or sequence does in fact require that the insulation material is spike resistant.
Okay.
So what they've done is they've designed this winding insulation. You got companies like SX and various companies who make this spike resistant wire, and we mentioned it in the intro, I think. But with that, they're basically building in technology, much of it proprietary, to dissipate that spike, almost like
see.
filtered or like a reactor would, get it removed so it's not creating damage. So yeah, it's the PIs definitely change differently, which is why, even though you have standard IEEE 43 set points, which we'll discuss a little bit,
Yeah.
you have to a lot of times change those set points as it pertains to different insulation systems, whether they're low voltage dip and bake processes versus actually, full-blown VPI, vacuum pressure impregnation. Those values are going to change.
Okay. So we mentioned earlier about heat is the number one cause. Most insulations have like a heat rating, Class B, Class F, Class H, 130, 155, 180 degrees Celsius. If you exceed, there's a rule of thumb. What is that rule of thumb like? If you exceed that, what potential bad things can happen?
So the rule of thumb that everyone should know is that 10-degree rise above the design temperature reduces the life in half, right? And that's a big deal.
That's significant.
It is significant.
How long do motors normally last?
Well, there's a couple things that we use to determine that, right? And although you talk to the average person in a good, clean environment, they expect 20 years out of a motor.
20 years out of a motor, maybe.
You talk to other plants that aren't in such a clean
Well,
environment.
you go into some places that have like a 1960s motor that's still running today.
Yes,
And that goes back to the construction.
It really does. Massive iron. It's just a completely different construction process. Of course, they used to burn those motors out in a bonfire out in the back of the motor shops too. So
True.
that's kind of a big deal.
I have seen motor shops like in some of the Asian Pacific countries that I've been through where they have torches on the side of the road and burning the windings
do
out.
what you got to do to get it done.
Do what you have to
different
do.
Time, different era, but so yeah, that's a big deal. That whole process takes quite a bit of process, and there's an efficiency issue that comes in play. But when you talk about what kind of environments create that 10 degrees rise above the design temperature, it doesn't take much. The way motors are built today, again, you can't even lay your hand on the motor. It used to be the rule of thumb was if you can put your hand on it for 5 seconds, it's okay. I know that's very generic.
Right.
And today that's out of the question. I would suggest you not put your hand on a motor without understanding how hot it can be today, because it's so much hotter. So yeah, heat, again, big killer. Let's keep the temperature where it's supposed to be. That doesn't mean that you wash a motor down and to keep it cool. You've heard of the wash down motor?
Wash down motor.
Wash down motors don't mean wash it down. That means that there's a process that they do wash down, but that doesn't mean wash the motor down.
There's been many meat facilities that you could go in and say,
Indeed.
You can see some.
You see the actual, like the box fan sitting in front of it.
Yeah.
That's
Blowing air.
external cooling. I guess that's one way to get it done, but you probably ought to understand, what the design of the motor is and why they feel like it's too hot.
Sure. So now, what types of tests are required for say, new motors?
Right, you mentioned new, which is important, and we always
Yeah.
try to revisit the quality assurance, the cradle to grave, right? So with a motor in the shop, there are a variety of tools that can be used to verify the asset health. Specifically, your willingness to hit it with a higher voltage, with a potentially more destructive voltage, it's a little bit more acceptable at a shop level, right? So we talk about, obviously, you're always going to rely on the old faithful RTG test, right? Resistance to ground, or megometer is a good reference, right? So that's the number one, very accepted, very often utilized. Again, in the shop environment, you're going to see surge testing and high potential testing applied. Again, those are under pretty strict guidelines.
Yes.
Clean and dry winding insulation systems in the shop. You're going to find that situation. You don't always find clean and dry in the field. In fact, very often you don't find it. And so that being said, what you want to be aware of is that, be smart about how you're applying this technology. High pot specifically, there's DC high pot, there's AC high pot. We'll accept a DC high pot, as far as a lead up or a quality assurance test. But when it comes to an AC high pot, that's very specific, very manufacturing driven, and be very careful with that. So RTG, surge testing, high pot, these are the kind of the standard from the cradle quality assurance on through, various stages of life.
What about an in-service motor? How should that be tested?
Right, so an in-service motor, this is where you're going to fall back to the tried and true RTG testing, PI testing, the stuff that you can do in the field. It's current controlled. You're not situation. You're not creating a stress environment. You're not over voltage testing that. Those are things that you normally rely. Over voltage is usually left at the shop.
Yeah. So a new motor, you're saying good QA. Let's over voltage test it. But once it gets into the field, RTG testing, capacitance to ground testing?
Absolutely. That's a great tool related to insulation. A little bit about the capacitance side of thing. When you're doing capacitance measurements, it's an AC test signal. Okay. Earlier I mentioned AC high pot, DC high pot.
Yeah.
Well, AC high pot is far more sensitive to insulation integrity issues, but it's also much more destructive, right? So now let's get into the low voltage or the high frequency situation that we're talking about. In the field, you can do RTG testing and follow the IEEE 43 guideline, which says, you can do, like for a 460 volt motor, apply 500 volts, no problem. If you're on a 4160 volt motor, apply 5,000 volts, no problem. But when it comes to capacitance, right, now we're talking low voltage. We're not talking AC high pot levels. We're talking very low voltages, but very high frequencies. And the nice thing about AC is it's more sensitive. So you can see things very early. We apply it in a low voltage scenario, it's differently, like say, than the power factor tip-up or things like that, and we apply that in a way that it actually allows early indications of contamination or insulation problems without the destructive nature of an AC high pot.
So capacitance to ground, then, if I understand you correctly, it's inverse to resistance to ground. So if our resistance to ground is going down, we assume capacitance to ground would go up.
Correct. Think of a capacitor, it's two plates and a dielectric median, right? So if you've got the copper wire as one of the conductors, you've got the case of the motor, which is susceptible to contamination, and the surface of the winding as the other connector, and then the insulation material is the dielectric. Well, as you contaminate the surface of that motor, you're increasing the plate size of one of the plates, and as a result, the capacitance goes up. But on a DC applied voltage measurement or an RTG test, more contamination, more conductivity to ground, resistance goes down, where the capacitance goes up. So very inversely related, proportional.
So you mentioned test voltages. What are the test voltages that if I have a 4160 volt motor or a greater than 12,000 volt motor, what are the voltages that I can use to apply a resistance to ground test to?
It's the $1 million question. We get it all the time.
Yeah.
The nice thing is most of the technology you're going to be utilizing, if it's computer driven and it's got a pre-existing set points, that's going to be a setup for you, which is really good. But in the event that it's not the case, you're going to want to refer to the IEEE 43 standard. It is you might say the golden book for
the pinnacle.
It is for the insulation test world, and it's for the most part it breaks down everything you're just asking. So if you're on a low voltage motor, they're going to recommend 500 volts. Okay, that's for trendable, asset health type testing of the insulation fault zone. Once you get up into the, let's say the 2,500 to 5,000 volt level, well, now you can go anywhere between 1,000 and 2,500 volts to actually trend and evaluate the asset health from there. And even greater than 12,000 volt motors, we're talking 13.8 kV, all these big,
so very larger motors.
Larger medium-sized voltage motors. now we're good. They're going to recommend between 5,000 or 10,000 volts for standard reliability and troubleshooting.
Because you're using them as a trend, right?
Trend is your friend, and this is no different than insulation. You don't need to be over voltage testing insulation when you're able to trend it. If you can't trend, then you have to fall back on more likely an over voltage test to try to get through a troubleshooting scenario. But initially, trend is the way to go.
So we know the resistance to ground test is normally around 60 seconds, a spot check of the insulation. But we also have, and you mentioned this a little bit earlier, is what we call a polarization index. But we also, the polarization index profile, kind of a graphical representation of the polarization index test. Can you explain the differences between a polarization index profile and a polarization index test?
Absolutely. We kind of hinted earlier that the polarization index test itself is a steady DC voltage applied to an insulation system, and you take the 10-minute and you divide it by the 1-minute values. Well, that should be between 2 and 5 for a healthy insulation system. One thing we've learned is that just looking at 2 incremental points on a polarization index test may not be sufficient. It may not, and often isn't, right? And so what kind of was born out of the whole polarization index test, with the onset of programmable, programs that actually store every data point on a graph, is what we call the profile. So it became very important not just to have a good PI or an index value, but also to have a good profile. If the profile is erratic and jumping up and down, and it goes down to a low value, then charges back up, and down and charges back up, that is not a healthy insulation system. Right. And so we rely as much on the profile as we do the index value when it comes to the PI.
Sure. And now tell us, what's the rule of thumb for back-to-back resistance testing? Like if I was going to do hold a voltage on the motor for 10 minutes. Right. How long do I have to wait?
You know where we hear this a lot? Is in tech support.
Yeah.
Yes, because what will happen is someone does, they don't wait at all. They go immediately back to back and they see completely different profiles, right? Why is that? Well, because the general rule of thumb is you need to wait as much as 4 times the charge for it to dissipate.
So if you had a 10-minute polarization index,
you really shouldn't test it again in that same test environment, i.e. another polarization index test, for 40 minutes. That's hard to do. That's a long time to wait, right?
A long time to wait.
So most people, do a variety of things. They try to discharge the motor and try to get it past that. Hopefully, they don't need to do a lot of back-to-back tests, but they will sometimes do a step voltage test in conjunction with the polarization index test, and that's something that people do. It's something that you need to be aware of. When you charge this insulation, you're basically, that DC voltage is aligning the molecular structure of the insulation, creating an opposing charge, which is why the actual current drops off. So initially there's a lot of current that's flowing through the insulation, and then eventually as that charging current or that charging voltage is in opposition, it drops off and the resistance value stables out.
So tell me the difference between a polarization index test or a polarization index profile versus a step voltage test.
Good question. So a step voltage, and now we're jumping kind of from the IEEE 43 standard, again the primary go-to standard, into more of the 95 standard. And the step voltage can be performed in a couple different ways. The most popular is a consistent time step voltage. So you hold a certain voltage, let's say 1,000 volts for 60 seconds, and you watch what the current does and how it responds.
Right.
Then you go the next 1 minute, you're going to go to, let's say, 2,000 volts, and then 3,000 volts. So you step up in given increments, in linear increments, and watch to see whether the current responds the same way.
Now, should you do one then the other? Do you have to do a PI then a step voltage test, or is it recommended to do that?
It's highly recommended. And again, it's nice if it's automated. It'll just go straight from the end of a PI straight into a step voltage test. But you got to be smart how you do that. The main thing they don't want you to witness in a step voltage test is all the absorption effort, right? They want you to be through that. They want you to get through the absorption test, which is a PI. PI is going to stabilize the absorption. It's going to be, flatlining, and that's when you go into a step voltage. So if you, let's say, do a PI to 500 volts, right, and then you start at 500 volts on the PI and go 500, 750, and on and on and on. You might jump up at a 250 volt increment. You might jump up at a 500 volt increment, and so whatever the right value is to get about 10 minutes of step voltage testing, that's what you're going to do. And the current in a healthy insulation system will go up linearly with voltage.
Okay.
If it's nonlinear, you see a sudden increase. Say you go from 3,000 volts to 3,500 volts, and that current jumps up, non-linearly, then now you're looking at a breakdown that you need to understand. The test will secure itself. If it's a good test, it should secure itself. You'll see it and go ahead and secure it yourself.
So what if you get a low resistance to ground measurement? Let's say you do a standard test and you just get below an IEEE 43 setting. What are your steps? What are your troubleshooting steps to solve the issue?
Great question, and similar. If you go back to the last podcast, I'm sure everybody heard that. We called out a divide and conquer approach, and it really becomes no different when it comes to insulation as well. We want you to separate systems, perform the necessary insulation test incrementally with the system segregated, find out what the root cause is.
So, no, I'm going to put you to the test again. We've got a interesting case study here that talks about insulation and actually variable frequency drives, and here's the problem. They came to us and they said they had 4 variable frequency drive failures within a short lifespan, all within 3 years. The electric motor recently was refurbished, okay? The motor in question was refurbished. VFD always replaced the new components at a cost of $45,000 each.
And they're expensive.
Frequent trips of the motor causing additional process problems.
We call those nuisance trips.
Nuisance trips.
Yes.
So we're brought out, this technician was brought out to the motor in question, and the first thing he did was do a standard test and look at resistance to ground, and saw that it was about 145 megohm on a newly delivered refurbished motor.
Right, and that's important because if you go back to the IEEE standards, it'll say a form-wound coil should be 100 meg for continued operation. Now the important phrase there is continued operation. In other words, they're saying if you got a motor running, and you shut it down to do this RTG test, and it's above 100 meg, then you could probably continue to run it. I can tell you this, when you get a new car, a brand new car, do you accept a scratch?
Never.
Never, right? But if it's a used car, you're going to be a little more flexible, the average person.
Well, in today's market, the used car market is not favorable to anybody. If you need a used car right now, you're in a world of hurt.
So expensive.
It sucks right now. You're paying extra money for it. Painful. If you can wait, but if not, hey, that's the situation you're in. But if in this day and age, I might accept a scratch.
I think I would too, right?
As long as it runs.
A couple maybe. But,
You're right.
So a motor, however, if you've gone through a refurbishment, cleaned, dried, tested, there's no reason for you to have 145 meg on a motor, right? That's just unacceptable when you expect hundreds of gigs from a newly refurbished motor.
And they ran a polarization index on this as well, and it ended up at 400 megohm after 10 minutes of holding a voltage to the system.
And the profile?
It was rather erratic. It wasn't. It was more. It definitely didn't float up towards infinity like you would want to see.
And there's some power here, right? Because if you had told me, hey, we got a 400 meg polarization index test, and it was a perfectly smooth, gradual increase in PI, the way the textbook PI should look, I would be more willing to say, hey, we're probably okay for a while, let's run this. I'd be a little concerned about the amplitude, but I'd be a little more willing to run it. But you tell me it's erratic, rising and falling, now I'm starting to be concerned about surface contamination or moisture, which is a big issue.
So what should we do there?
Well, again, separate, divide, and conquer. I would separate the motor from the cables and see which one has the worst reading. Remember
put the cables, tie the cables together.
Oh, that's a very good approach. A lot of times you separate the motor and the cables, and because it's 3-phase, if you tie 3 ends of the cable together, you can do one test and test them all. If you don't have the ability to tie those together, you're going to want to do individual resistance to ground tests on each cable and make sure to see if they're equally, high enough to accept them. So
when we did that, the cables stayed low, but the motor itself went up to about 1.7 gigohms. So it went from 145 megohm to 1700 megohms.
This reminds me of the C story in podcast number 2, I think, or 3, where the cable can be an absolute issue. I can tell you that more often, people they get falsely comfortable that the cables, they're just cables. They don't go bad. They're not the stressed element. They're not rotating, But in reality, the cables play a key role and need to be evaluated in every situation. And so by separating those two, recognizing that the low value stayed with the cables, it allows us to now, let's check off the motor to make sure it's okay, and if it is, we move on.
So we check the motor is good. Now we're going to really highly focus on the cables. They were able to go in and start to look for any type of, the one place you go to is the conduit, right? You go to see if there's water in the conduit, that cable is laying in water. But they didn't find any. They did find some scratches on it. So they decided to go ahead and pull the cables out, replace it with new, and then lo and behold, as they laid the cables on the ground, due to gravity drain, you see water coming out of the cables. It had wicked up into the cable system.
It's amazing how water finds a way.
It's very intrusive.
It is. In fact, that it was almost hiding in the cable runs. And the other thing is, sometimes you look at those connection boxes and there's a rust line halfway up. Did that come from the manufacturer?
That's very visual, and you can see that immediately. You kind of know, hey, this was a problem. We had water in here at some point.
Well, and what ends up happening is, of course, a lot of times they're taping, they're sealing up the cable to the actual lug. So it holds all that water in there, and without actually, taking it out of its horizontal or vertical environment and putting it, where the gravity can pull it out. That's a big deal. And so this is a good situation where the water contaminating the cables are actually showing up in the polarization index test. So you see that erratic variation. You're worried about conduit or the conduit water, as you mentioned, ends up being in the cables. Great find. And which brings us back to the drive issue.
It almost brings us back, to the power quality where the manufacturer had said, check your ground.
That's a perfect link, because, they say that for a reason, and here's a perfect example. With that ground wall, which is a neutral reference for the drive, as you start to manipulate that, it's partially grounded, it's fully grounded, that kind of thing, and that water coming in and out is going to change the value. Well, the neutral reference on the drive will also vary, causing misfiring. Now, what paid the price here wasn't the motor, it was the drive. So in this situation, our power circuit or insulation fault zone of the cables were killing 4 drives at the price of, $180,000?
Yeah, close to that.
Extreme. So great find and great recovery.
Well, it just goes to show you that it may not jump out at you. No. So you have to go and dig a little deeper, and in this case, find that the water actually sucked up into the cable itself. It wasn't in the conduit. So, Noah, that brings us to the end of this podcast, which always we want to thank you for your expertise.
Thank you for the opportunity to share.
And, it brings us for the next one that we're going to go to. Our next podcast that we'll be bringing up is this is the one where if it goes bad, there's no coming back.
I see. It's the stator fault zone.
You have to bring it. So a stator, you always have this cool little thing that you talk about with the stator. What do we try to do with stators?
So, like you mentioned, if the stator fault is identified, it is at the end of the PF curve, right? Yeah. So of all the fault zones, this is one you never want to reach. And all the testing that you do in reliability, whether it's vibration, motor testing, thermography, everything you're doing is to try to identify conditions conducive to a stator fault, fix them.
Almost like your health.
Exactly.
You're trying to eat correctly, exercise, get a good night's rest, all those things, so that because the end result, if you get heart disease or something of that nature, there's not an easy fix for that.
No, those muscles don't recover.
So think about it that way. It's eating right, it's maintaining your blood sugar, all those things that the doctor's telling you to do. It's the same thing for this.
It absolutely is.
Don't make sure the power circuit doesn't have excess heat that plates out in the stator. Make sure that the turns are correct. Make sure there's no solder connections in that stator, which we're going to get into and share in depth, but we want you to join us for that, okay? So, as always, thank you, Noah, for your expertise. Once again, that's Noah Bethel, the VP of Product Development. I am Todd Gunderson, the VP of Sales and Marketing. And we thank you for listening and hearing what we have to say. We hope it's been informative for you. And as always, we look forward to seeing you again in our next podcast. Maybe not seeing you, but listening to us in the next podcast. That'd be appropriate, right?
Absolutely.
Come join us in sunny Tampa, Florida. Until then, we thank you for everything. Thank you for your time, and stay safe, and I hope you have a great day.
Thank you for joining us for this episode of the Todd and Noah Show. We'll be back for another episode very soon. In between, we hope to see you in the Mobius Connect online community, where you can network, learn, and share with Todd and Noah and other industry professionals at mobiusconnect.com, and we will see you there soon.